All right, so today we are talking about the difference between linear, quadratic, and exponential functions. So first off, we're going to talk about a linear function. So remember, the equation is y equals mx plus b, where m is the slope and b is the y-intercept, right? So if I've got an example where I've got y equals x minus 3, okay, how did the tables look and how did the graphs look? Well, graphs of linear functions are always going to be straight lines. Okay, we talked about this the other day. And the table, what it's going to have is going to have a common, what we call first difference. Okay, so what that means is when I find the difference in the values, I'm looking at the first difference. Okay, so every x, let's see, we're going up by 1. The first difference would be between the y values. So between -5 and -4, I'm adding 1. Between -4 and -3, I'm adding 1. Between -3 and -2, I'm adding 1, adding 1, and adding 1. So that's what a first difference looks like. And we're going to see what a second difference looks like in a second. Maybe that will help make more sense. Okay? So we look at the change in the y values. Okay? When you see that triangle, that represents change in y. And we look at the change in the x values. Okay? And the change in the y values must be common first difference. Okay, when we say difference, that means adding or subtracting. Okay, not multiplying or dividing. That's something different. So next, we've got a review of our quadratic function. So standard form is y equals ax squared plus bx plus c, where c is the y-intercept. Okay, and then remember, we do have two other forms. So we may see our vertex form, which was y equals a times x minus h quantities squared plus k. Okay, that is a quadratic. It has an exponent of 2. And then we also will see the factored, and that is y equals a times x minus x1 times x minus x2. Okay, so all three of those forms are quadratics. Okay, quadratic equations, for this example, I've got y equals x squared minus 4. They have a common, what we call a common second difference. So when I look at my y values and I look at what's happening, okay, from 0 to -3, I'm subtracting 3. From a -3 to -4, I'm subtracting 1. From -4 to 3, I'm adding 1. From -3 to 0, I am adding 3. And then from 0 to 5, I'm adding 5. Okay? Then the second difference is now with these first differences, what's the difference between those? So to get from -3 to -1, I had to add 2. To get from -1 to +1, I had to add 2. To get from 1 to 3, I add 2. And to get from 3 to 5, I add 2. So this is the second difference. Okay, so you have to do it twice. So if you do it the first time and it's not a common difference, it's not a common ratio, try the second difference and that may be a quadratic. Okay, and the graphs are always parabola or U-shaped. Okay, so that is quadratic. Common second difference and U-shaped. Okay, last is exponential functions. These are ones that we've been talking about recently. Okay, A is the y-intercept or the initial value, and R is the common ratio. Okay, So exponential functions, what they look like, I've got this example, y equals 1 times 2 to the x. They have a common, which I already have that word up there, but it is ratio. Okay, that is multiply or divide. So when I look at this one, I've got 1/4 to 1/2 to 1 to 2 to 4 to 8. Okay, I'm not adding something consistently. And if I were to look at the second difference, it would also not be the same. So you just think about, what am I doing every single time? How do I get from 1/4 to 1/2? 1/2 to 1 to 2, 4 to 8, while I'm multiplying by 2. Okay, so that is my common ratio. And graphs are always going to look something like this, where they've got like a curve. Now remember, it could look like that. It could look like this. And it could look like this. Okay, we've got all those different options, but they have that little curve that distinguishes them. Okay? So we're going to look at these three, and we're going to label them as exponential, linear, or quadratic. Well, this first one is a straight line, so this is going to be linear. The second one, if we think about kind of what we've got, it goes up, comes back down, that would be quadratic. And then lastly, it kind of is coming to like a curve so far, so that is going to be exponential. Okay, so given a table, state which model best describes the data, exponential, linear, or quadratic. So when we think about these, exponential has a common ratio. Linear has a common first difference. And quadratic has a common second difference. So first I'm going to look to see, am I adding something consistently in this example? Okay, so am I adding something each time? Okay, so we can do that by, let's see, what's the difference between 24 and 96? I can do that by doing 96 minus 24. Okay, and it's 72. So to get from 24 to 96, thinking about a first difference, I have to add 72. Okay, to get from 96 to 384, am I adding 72 again? No. 96 plus 72 is 168. Okay, so I know that it is not linear, not a first difference. Okay, now let's check to see if it's exponential. Does it have a common ratio? So I can do 6144 divided by 1536, just like how we used to find our common ratio. Okay, and I've got 4. Now, if I keep going through, it has to be consistent. So I go 1536 divided by 384. Well, that's also 4. And then 384 divided by 96. That's also 4. And then 96 divided by 24. Oh, it's also 4. So that means what's happening every single time is I'm multiplying by 4. So this must be an exponential because it has a common ratio. Okay? So another one, this time I've got a golf ball and its height. Okay? Let's look to see if there's a first difference. Well, I can kind of see right off the bat that there's not a first difference because from 4 to 68 is 64, and then 68 plus 64 is not 100. Okay? Let's check to see if there's a common ratio. So I do 68 divided by 100. That gives me 0.68. And then, wait, the next one would be 100 divided by 100. Well, that's 1. So there's no common ratio. There's no common first difference, which means let's find the second difference. Okay, so 68 minus 4 is going to get me 64. Okay, then to get the next difference, I do 100 minus 68. That one's plus 32. Okay, and then from 100 to 100, that's plus 0. And then from 100 to 68, that is a minus 32. Okay, so that's the first difference. Now, what's the second difference? To get from 64 to 32, I subtract 32. To get from 32 to 0, I subtract 32. And to get from 0 to negative 32, I subtract 32. So this one must be quadratic because it has a common second difference. All right. And then lastly, I've got boxes and reams of paper. Is this exponential, linear, or quadratic? Well, looking at it, does it have a common difference? Okay. I do 10 to 50. Well, that's 40. And then 50 to 200 is 150. And then 200 to 500 is 300. So at first glance, it doesn't look like it, but what's happening to the x values? Adding 4, okay? And then for this one, I'm adding 15, okay? And this one, I'm adding 30. So if we're thinking about like slope, okay, we calculate slope by doing our change in our y over our change in our x, and that would give us the common difference. Okay, so the reason why I didn't look at the other ones is because the other ones were just going up by 1, right? 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. This one, it is not. Okay, so if we do, this is x, and this is y, our change in y over our change in x. So it would be 40 over 4. Okay, well, that gives me 10. And now I want to make sure that slope is consistent throughout. So 150 divided by 15 is 10. And 300 divided by 30 is also 10. Okay, so for every one change in x, right? Every one change in x, I get 10 changes in y. So if I were to like add 1, my next one would be 2, and now I would have 20. Then 3 is 30, and 4 is 40, and 5 is 50. They just like skipped those spots. Okay, so you do have to pay attention to that change in x as well as that change in y. So this one would be linear. I don't even have room, because it has a common first difference or slope. Okay, slope and first difference represents the same thing. So next, write a linear function that models the data. Okay, so linear function is y equals mx plus b. Remember, slope is change in y over change in x. And we say that by using this Greek letter is actually called delta. So delta y, delta x are change in y over change in x. Okay, so let's start off by finding the change in y. And I'll do that one on the top because that's on the top of the fraction. Okay, because it's a linear function, I'm going to be thinking about like what am I adding each time. Okay, so to get from 7 to 8, I add 1. To get from 8 to 9, I add 1. To get from 9 to 10, I add 1. Okay, what about the change in x? From 0 to 2, I add 2. From 2 to 4, I add 2. And from 4 to 6, I add 2. So when I put these together to find my slope, I'm going to do my change in y, which is equal to 1, divided by my change in x, which is equal to 2, and that is my m, my slope, okay? And then my b is the y-intercept, which is when x is 0. So my b equals 7. So I take those, I put those together, and I get y equals 1/2 x plus 7. I find the slope, and I find the y-intercept. Okay, next, write an exponential function that models the data. Okay, so A is kind of our first point, and R is the common ratio. So I have to find the common ratio in order to write the equation. You do that by dividing backwards. So how do I get from 0.648 to 1.08? Well, I'm going to divide 0.648 divided by 1.08. And I get 0.6. Okay, and then I have to keep going to make sure it's consistent. So 1.08 divided by 1.8, and I get 0.6. And then again, 1.8 divided by the previous term, and I get 0.6. So that means my R is 0.6. My 3 is my A because that's my starting term, so I take those together. Y equals 3 times 0.6 to the x. And that's how I write an exponential function that models the data. Okay? Lastly, given the first two values of a numerical pattern, find the next two terms if it was linear and if it was exponential. Okay, so we're just going to do the first example. Okay, if it was linear, that means it has a common difference. Okay, so how do I get from 1 to 5 thinking about adding or subtracting? Okay, well, I have to add 4. So then to keep it consistent, I'm going to have to add 4 and add 4, and then that would be linear. So 5 plus 4 would be 9, and 9 plus 4 is 13, and that would make it linear. Well, exponential, I have to figure out what do I have to multiply by in order to get that next term. Well, I have to multiply by 5 in order to get from 1 to 5. So that means to make the rest exponential, I want to multiply by 5 and multiply by 5 again. So 5 times 5 is 25, and then 25 times 5 is 125. Okay, so it's taking the same terms, or the same first two terms, but one I'm thinking about what is my difference, what am I adding or subtracting, and the other one I'm thinking about what is my common ratio, what do I need to multiply by in order to get the next term. All right.